So let's discuss the normal form of a line. So this is another way of representing the equation of a line. So here we have P, which is going to denote the length of the perpendicular or normal from the origin to any given non-vertical line denoted by L. And alpha is going to be the angle between that normal line and the positive direction of the x-axis. Then the equation of the line is given by x cosine alpha plus y sine alpha equals to the length of the normal line, which is P. Let's try to understand this graphically. So here we have considered the xy coordinate plane. We have the line L. Now the line L, this is going to intersect the x-axis in the positive direction, let's say at the point A, and it intersects the y-axis in the positive direction at B. So we can say that the line segment AB, it's going to lie in the first quadrant, and we have another line which passes through the origin, O is the origin where the two coordinate axes meet, and it is going to be perpendicular on the line L. Now let's say it is perpendicular, that means it meets the segment AB at the point P. Now if the length of this perpendicular or the normal OP is denoted by P, and we suppose that it is also making some angle alpha with the positive direction of x-axis, then the equation of the line L, not the normal, the equation of the line L, that will be given by x times cosine of that angle alpha that the normal makes with the x-axis added to y times sine of the angle alpha, and this is going to be equals to the length of the normal. So that means in order to determine the equation of a line, so what we need here, we need two information. One information will be the distance of the straight line, or we can say the non-vertical line from the origin, the perpendicular distance, and we also need the angle that the perpendicular distance makes with the positive direction of x-axis. Okay, now this is not the only scenario. We have a couple of other scenarios as well. Let's look at them one by one. So in the second case, we have the line L intersecting the x-axis in the negative direction, let's say at the point A, and it intersects the y-axis in the positive direction, such that AB is the line segment that lies in the second quadrant of the coordinate system. And here we have the length, let's call it OC. So OC is the perpendicular distance of the line L from the origin, and this perpendicular length OC, it's going to make an angle alpha with the positive direction of x-axis. So that is very important. So here we take this obtuse angle, which is going to make an angle alpha, and it is making this perpendicular length OC is making an angle alpha with the positive direction of x-axis. Next we have the straight line L, which is going to cut the x-axis in the negative direction at A and the y-axis at the negative direction at B. So we have OC, which is going to be the normal of length P. OC is going to be the perpendicular distance of the line L from the origin, and here also we see that it's making an angle alpha with the positive x-axis. So that's very important. So with the positive direction of the x-axis. And finally we have the situation where the line L cuts the x-axis in the positive direction at point A and the y-axis in the negative direction at B. So OC is going to be the perpendicular length, and it is making an angle with the positive direction of x-axis. So here we can clearly see this is going to be the angle alpha. We have already mentioned that the equation of the line in each case is going to depend on the value of alpha and the perpendicular distance. But whatever be the case, its equation is always given by x cosine alpha plus y sine alpha equals to 1. So let's try to geometrically derive the equation of the straight line. So we're going to take the original case where we consider the line segment AB to be lying in the first quadrant. So to begin with, let us perform some construction. So we have the perpendicular meeting the segment AB at the point C. Now, in order to determine the equation of the line L, we're going to consider the locus of a point. So let's say as the point D having the coordinates x, y. And then from point D, we're going to draw a perpendicular on the x-axis. Now let us suppose that the perpendicular meets the x-axis at the point E. So here we are going to perform a construction. So we are supposing that the perpendicular DE, or you can say the line segment D, is going to be perpendicular on OA. Next, what we'll do, from this point E, we're going to draw another perpendicular on OC. Let's say the perpendicular meets OC at F. So here we have O or EF is going to be perpendicular on OC. And then next, finally, we're going to consider point D, and from point D, we're going to drop a perpendicular on EF. So let's say it meets it at the point G. So here we have DG, it is going to be perpendicular on EF. Okay. Before proceeding further, you might have a question why we are going through all of these construction, because what we are trying to do here is we are trying to find out the length P. P is the perpendicular distance of the line L from the origin. Now clearly P is given by OC, and we can break down OC into two parts as OF added to FC. So this is going to be our goal. So we'll have to find out the length OF and the length FC. Okay. So first what we'll do, we're going to consider triangle DEG. Now here in this triangle DEG, this angle GED, or you can say angle DEG, this angle is going to be alpha. Now why it is alpha? That's a very simple task to understand, because if we consider the triangle OFE, clearly angle FOE, that's alpha. Angle OFE, that's going to be 90 degrees. So what is angle G? What is angle E? That means what is angle OEF? This particular angle, this angle is 90 degree minus alpha. Fine. If it is 90 degrees minus alpha, and we know that DE is perpendicular to OA, which means that DEG added to FEO, they must sum up to give us alpha. Fine. So that is why geometrically DEF, this angle becomes equals to alpha. Now what we'll do, we're going to consider the triangle OEF. We have the triangle OEF. So let's take cosine of the angle alpha. So cosine of the angle alpha, that is going to be given by the adjacent, which is going to be OF, over the hypotenuse. So here hypotenuse is OE. Fine. So we can isolate OF, and that is going to be equals to OE times cosine of angle alpha. Now what is OE here? Now since we consider the coordinates of point D to be x comma y, so clearly the length of OE, this is going to be equals to x. So we can say that OF is going to be equals to x cosine of angle alpha. Right? So let's label this as number 2. So this equation, the equation for P, it's going to be equation number 1. And then next we are going to consider the smaller triangle DEG. So in triangle DEG, so this time we're going to consider sine of the angle alpha. So sine of the angle alpha, that is going to be the opposite, which is DG over the hypotenuse. So that's DE. So I can cross multiply to get DG. This is going to be equals to DE sine alpha. Now what is DE? Now DE, so DE is simply going to be the height of the point D. Now that is going to be y. So we have obtained that the length of DG, that is going to be equals to y multiplied to sine alpha. But we can also say here that DG, this is the same as FC. The length of DG, it is going to be the same as the length of FC or CF. So here we can say FC is going to be equals to y sine alpha, and let's call it number 3. So what we can do, we can now substitute 2 and 3 back in equation number 1. So that means equation number 1 now becomes P is going to be equals to x cosine alpha added to y sine alpha. So here we have successfully obtained the equation of the straight line. So in this approach, what we have considered the locus of a point D, which is going to lie on the line, the point D, and with the help of this locus, we were able to get the equation of the line. So this is one of the approach. There is another approach as well. There are several approaches. So one of the approach would be, so what we can do, we can consider the point C to be having the coordinate x comma y. Let's try to understand that as well. So let's consider the alternative way of finding out the equation of the line. So let us begin by considering the point C. This is the point where the perpendicular drawn from the origin meets the line L. So this, we're going to try to find out its coordinate. That's a very simple task. All you have to do is drop a perpendicular from the point C on the x-axis. Let's say it meets the x-axis at E. And then we have another perpendicular drawn from C which meets the y-axis, let's say at the point F. Fine. Now, what is the length of CE and the length of OF? Now, CE, that is the height, which is the y coordinate of point C, and OE, that is going to be x, which is going to be the x coordinate of the point C. That's a very simple sir. We can take the help of trigonometry, and the x coordinate, that is going to be p times cosine of alpha. The y coordinate is going to be p sine alpha. Right? So here we have obtained the coordinates of point C. Next, what we'll do, we'll try to find out the slope of OC. That's a very simple task. Slope of OC is simply defined as take the tangent of the angle that the line makes with the positive direction of x-axis. In our case, that's alpha. So tangent of alpha is going to be the slope of OC. Now that we have the slope of OC, we can also find out the slope of the line L, or we can say slope of AB. So slope of AB, we know that since slope of AB times the slope of OC, this is always going to be equals to -1, because two perpendicular lines, when we have two perpendicular lines, the product of their slope always equals -1. Since we have the slope of OC, so we can substitute slope of OC with tangent of alpha, and that's going to help us obtain the slope of AB. So slope of AB, this is simply going to be equals to -1 divided by tangent of alpha. We know that the tangent of alpha, that is simply going to be the reciprocal of the cotangent function. So our slope becomes negative cotangent of alpha. Fine. So now we have the slope of the line L. So we have the line L whose slope is known, and it also passes through the point C whose coordinates are known. So here what we can do, we can use the point slope form of a line, using the point slope form, and that is going to help us obtain the equation of the line. Now, what is the point slope form of a line? Let's say we have a point whose coordinate is known, and through this point we have a line passing. Let's say this is the point having the coordinates x1 comma y1, and the slope of that line, that is also known, let's call it m. Then the equation of this line L, and let's call it L1. Equation of line L1 is simply going to be y minus y1 equals to the slope m multiplied to x minus x1. This is referred to as the point slope form of a line. So here our point, the coordinates of the point C, that's p cosine alpha comma p sine alpha. We have the slope of that line, so we can use the point slope form, and the equation is going to be y minus y1. So y1 is going to be p sine alpha equals to the slope we have obtained as negative cotangent of alpha. That's going to get multiplied to x minus x1. So x1 is going to be p cosine of alpha. Fine. So let's further simplify. We're going to get y minus p sine alpha equals to, now negative cotangent of alpha times x, that's going to give us negative x cotangent of alpha. Add it, so we have negative times negative and negative, that will become positive. So p, now what is cotangent of alpha multiplied to cosine of alpha? We have cotangent of alpha times cosine of the angle alpha. Cotangent of alpha, that's cosine of alpha over sine of alpha multiplied to cosine of alpha. So what we get here is cosine squared alpha over sine alpha. So we are going to get p times cosine squared alpha whole divided by sine alpha. Now let's multiply throughout with sine alpha. So we're going to get y sine alpha minus p sine squared alpha equals to negative x. Now we have to multiply cotangent of alpha with sine alpha. So that's simply going to leave us with cosine of alpha added to p times cosine squared alpha. Okay, so let's rearrange the terms. We're going to transpose negative cosine alpha to the left hand side, and that's going to give us x cosine alpha. We're going to keep the first term on the left hand side, which is y sine alpha, as it is, y sine alpha. And then we're going to transpose negative p sine squared alpha to the right hand side and combine with p cosine alpha. So here what we can do, we can take p as the common factor, so that's get multiplied to sine squared alpha plus cosine squared alpha. Now that's a standard identity, sine squared alpha plus cosine squared alpha, that's always equals to 1. So finally we get x cosine of alpha plus y sine of alpha, this is going to be equals to P, the perpendicular distance of the straight line from the origin. So this is also going to give us the same equation. So whichever approach you use, both of them are giving us the same result. So this is going to be the equation of the straight line L, which is at the perpendicular distance of P from the origin, and the perpendicular length or the normal makes an angle of alpha with the positive direction of x-axis.